Okay, so let's get started. Uh, the lecture before last, we were looking at frequency response, and we had seen the lower cutoff frequency of a common emitter amplifier. And we had seen that what you need to do is derive an expression for cutoff frequency due to each one of these capacitors here, the capacitor over here, the capacitor in the emitter, and the capacitor in the collector. Each one of them you calculate separately. And if one of the frequencies happens to be much larger than the other, then the 3 dB frequency is basically due to that particular capacitor. And you can say approximately FL equal to FE here, in this particular case here. In this particular, I was trying to show you in the last lecture that typically the frequency due to the emitter bypass capacitor is much larger than the frequencies due to other one. And so we had, we were making a simplified case here that assuming it becomes easier to show through equations if you assume that RS is negligible. And I'd written here no load. It basically doesn't mean RL equal to infinity. The implication was RL is much smaller than RC, let's say. Then you can neglect RL in comparison to RC, and you can say that. Okay. And in general, what we can see here is, no load is a little bit confusing here. All we can say is if I look at this particular expression, FC will always be less than or equal to 1 by 2 pi CCRC here. Okay, so we can always say that. And we have expressions for FB, FC, and FE here. And it's easy to now look at these expressions and show that FE is under these constraints beta times FB here. And compared to the collector also is much larger here. All right, so one can show that if the capacitors are comparable, all emitter, base capacitor, collector capacitor, and emitter bypass capacitor, if they're all comparable in magnitude, then typically you'll find that the emitter frequency, the 3 dB frequency associated with the emitter is much larger than the other one, and lower cutoff frequency is determined by the emitter bypass capacitor. So that was lower cutoff frequency. So let's look at now. Yeah. That is, it depends on how accurately you want to calculate. It's just an approximation, yeah. Somebody may say 4, somebody may say 10. Depends on how accurately you would like to say that, let's say the cutoff frequency is equal to FE. Okay. All right, let's look at the upper cutoff frequency. For this case, we have seen earlier that what we do is the external capacitors that you have, the capacitors at that particular frequency, are basically like shorts. The impedance is much smaller. For example, the collector capacitor, if you look at the impedance at higher frequencies, is much smaller than RC or RL, and therefore it's a short here. Similarly, the emitter bypass capacitor is a short, and base coupling capacitor also is a short here. So upper cutoff frequency we know results from transistor capacitances here. So we have C pi and we have C mu here, and we have CCS here. So these are the capacitors which will determine the upper cutoff frequency here. So this is the hybrid pi equivalent circuit we obtain, or the equivalent circuit of a amplifier we obtain at higher frequencies. What we can do is, emitter resistance goes away because the bypass capacitor was there. Bypass capacitor takes it away. Okay. So what we can do is, whenever you obtain a circuit, you remove, you put in all the elements that you think are relevant. What you should do is simplify it. So for example, if I look at this particular expression, there's no point, this particular circuit, there's no point in keeping RS, RB, B, and all of that as 3 separate resistors. I can, take a Thevenin's equivalent at this particular node and, lump up all of them. So one can get one single resistor, which is RS parallel RB here, in series with RBB here. So I can lump it up in one single resistor. Similarly, no point in keeping RC and RL as 2 separate resistors, lump them up in one single resistor RC dash here. So we obtain then a simplified circuit, which is shown here. So because we have taken a Thevenin's equivalent at this node, I don't have VS directly, I have VS dash, and I have RS dash, which is given over here. And then I have R pi, C pi, C mu, GMVB. For simplicity, what I've done is, I've said that this is an important capacitor, but in a simplified analysis, we are going to neglect this here. Okay. So CCS I have neglected. One can take that into account also. It's not difficult. but in this case, we have omitted it here. So we have two capacitors, C mu and C pi, and we have this particular circuit, and we need to solve it in order to get the upper cutoff frequency. So our procedure, one of the procedure was take one capacitor at a time. So when you take C pi, what you do is you open circuit C mu, find out the net resistance that C pi sees, or in other words, find out the time constant due to C pi. Similarly, open circuit C pi, find out the time constant due to C mu. So you get two time constants, sum them up and take inverse of that, and that will give you the 3 dB frequency here. Before I do that, let me again tell you the accurate approaches that you write down the transfer function. You write down what is V0 here by Vs dash here. So you write down the transfer function, and if you do that, this is what you obtain. Okay, so it will take you a little bit of time. It's not that complicated, although the expression looks, a little bit daunting, but it won't take you too much time to derive this particular expression. So if you see here, what you notice, the denominator is a second order, is a quadratic expression. Okay, first term is a constant, second term is s dependent, and the third one is s squared. Quadratic here basically means that I have two poles. If you factor it out, you will get two poles in your system. And in the numerator, I have one s term. If you factor this out, it denotes 1, 1, 0. So if I look at my transfer function, I have 1, 0 and two poles in my system here. So this is what I'm saying. If you look at the denominator, you can write this as 1 by s plus p1 by 1 plus s by p2, multiply it together, and this is what you get. Now, if you factor it properly, you'll get p1 and p2. Sometimes what people do is they assume, and it's true, that you have a dominant pole in the system. Dominant pole meaning that p1 is, let's say, much lower than p2. That's what dominant pole means here, that it occurs at a much lower frequency than p2. So what happens is, if p1 is much less than p2, then the second term, you can write it as 1 plus simply s by p1. And in the last term, we keep it as it is, s square p1 by p2. If you make that approximation, if you have a dominant pole in your system, then what you can do is, if you just compare the factor before s, that gives you p1 straight away. All right, so you don't really have to solve the quadratic equation. You get directly by looking at the denominator. You get where is the first pole, p1. So you get it by looking at the the factor before s, and the factor before s square gives you p1 and p2. And so you've already found p1, and therefore you can find p2. So it becomes very simple. And fortunately, it turns out that in many of these systems, you do find that you have a dominant pole. One pole is at a considerably lower frequency as compared to p2. So the approximation then is fairly accurate here in many cases here. So that's how we obtain p1. Okay, we obtain p1 and we obtain p2 by assuming a dominant pole here. And the 0 is nothing but when you equate this numerator to 0 here, and you find that there's a right half plane 0 here. All these are on the left half plane, poles are on the left half plane, and 0 is in the right half plane here. So this is what you obtain. Two poles, p1, p2, and 0 here. And as I've been saying that many times what happens is, this pole is a dominant pole. It occurs at a much lower frequency as compared to, let's say, p2. And similarly, if you compare these two expressions, if you put in values, you'll find that the 0 occurs again at a much higher frequency. So the idea is that I do have two poles in my system, 1, 0 here. But to the first order approximation, I can assume that I can neglect this because it occurs at a higher frequency. I can neglect this because this also occurs at a higher frequency. So you can model it as one pole system. And when you have one pole, then this one is nothing but the 3 dB frequency. One pole means it's like a simple RC circuit. So it's like a 3 dB frequency here. So under dominant pole approximation, then pole is nothing but it's a break frequency, the place where things start changing with frequency here. So we get the upper cutoff frequency from here. So what I'm pointing out is one way of getting upper cutoff frequencies is you go to the transfer function, and the transfer function will have several poles and zeros. If you have a dominant pole, then finding the dominant pole becomes relatively easy once you have the transfer function, and your upper cutoff frequency is simply the dominant pole. Okay. If you don't have a dominant pole, then of course things are complicated. things are complicated, it becomes difficult to find out an expression for omega h. Okay, so that's the transfer function approach. Yes. In this we have 2 poles and 1 0 in this common emitter amplifier. It depends on the amplifier, what the amplifier is like. You may have more, obviously. So the other method is, as we said, our simplified method is open circuit time constant. And as you can see here, this method becomes complicated to use, and I can use it for example, in this case, I have a single stage amplifier. If I have 2-stage amplifier, one stage followed by another stage, and the next stage has its own CPi and its own C mu and all of that, writing a whole transfer function and factoring it becomes difficult. Okay, so except for single stage amplifiers, the method becomes difficult to use. Okay, and therefore, what is more convenient is the open circuit time constant approach. It's not going to give us the most accurate answer, but as I said, our purpose is to capture all the important parameters in a closed form expression, an expression which tells us what really affects my 3 dB frequency here. So our approach then is, remember, this is what we'll do. We'll take one capacitor at a time, let's say CPi, find out the effective resistance seen by CPi, and that we are calling it RPi. Okay, and so this is the time constant associated with my capacitor CPi here. Next, we'll take C mu, find out the effective resistance seen by C mu, and calculate its time constant R mu C mu. And omega h is nothing but sum of the time constants here. And fh will be 1 by 2 pi, this value here. So all you have to do is upper cutoff frequency, take one capacitor at a time, and find out what resistance it sees, sum them up, and just get the upper cutoff frequency. Okay, so this is the method that we'll be using here. So now so we open C mu, and the question that we are asking is, what is the effective capacitance seen by CPi? The general method, of course, is you remove CPi, you attach a source Vx, find out what is the current Ix flowing, and Vx by Ix will give you the resistance seen by CPi here. But in this case, it's straightforward. We can see here the resistance seen by CPi is resistance looking here, and it's nothing but Rs dash parallel RPi. So we can see it straightforward, and that's the resistance here. This side doesn't matter. Okay. All right, so this is okay. C mu is more a little bit more difficult here. So again, when I'm calculating C mu, I remove CPi, open circuit it, and since I want to know the resistance seen by C mu, as I said, we put a source Vx, and we look at the current Ix, and you need to solve this circuit. It takes 2-3 steps to solve the circuit, and you get R mu, which is Vx by Ix, is 1 by Rs dash parallel Rpi, 1 by 1 plus GMRC dash plus RC dash here. So that's the resistance that you get here. Okay. So I've skipped the steps, but you can easily do that yourself and get the value of R mu. So my 3 dB frequency then becomes, all that I've done is CPi multiplied by RPi, the capital RPi, and C mu multiplied by this, and we get a omega h, which is given by this expression. Okay. Now, as you can see here, if you go back and look at our method, calculating resistance for CPi was fairly easy. Calculating resistance for CPi is very easy, and it just turns out to be Rs dash parallel Rpi. Calculating impedance for C mu was more difficult because it is spanning both input and output, and it requires more effort here. And also, you obtain an expression for R mu, but this method doesn't give you insight into what is really happening here. You get an expression, but why is R mu like this? You don't get that much idea. Okay, so a technique that is commonly used, a theorem called Miller's theorem, is used to simplify. And so this is a very interesting theorem. Let's understand what it says. So the idea here is you have an amplifier, and it need not be an amplifier, but we are talking in the context of an amplifier here. And let's say there's a capacitor connected between input and output. All right, input and output here. And as I just said, a capacitor connected between input and output causes a little bit of a problem in terms of calculating resistances and all that. And it does, a little bit difficult to understand how this capacitor is affecting my 3 dB. What helps is that I can take this particular capacitor and break it up into 2 capacitors here, one at the input and one at the output. And if I look at the circuit from this side, whether the capacitor CF is connected here or a capacitor CMI is connected here, it doesn't make a difference. That's what we mean by equivalent circuits. If I look at from this side, whether CF is here or CMI, M meaning Miller's capacitance here, I means on the input side. So Miller's capacitors on the input side here, it doesn't make any difference. These two circuits are equivalent. There's no way by making any measurement here or any measurement here you can tell whether the two circuits are different. That's the idea of equivalent circuits. Similarly, when you look at it from the output side, whether the CF is connected between input and output, or you connect a capacitor here between the output and this common terminal here, you can't tell the difference. So that's the idea, that we are going to take this capacitor CF and break it up into two capacitors here such that the two circuits are equivalent. So when you look at it from input or output side, there's no difference. Okay, so how do we calculate CMI? Well, the idea is when I look at it from the input side, what do I mean by that? That when I apply a particular voltage, I get a certain current. And similarly, when I apply the same voltage here, I should get the same current. So if I equalize the current in two cases, the two circuits are equal, electrically equivalent. Okay, so that's what we are doing. If we look at this particular current here, input current, the current has two components. One, of course, will go into the amplifier. The other one will go up through CF. And the current that goes through CF is V in minus V0 divided by the impedance of the capacitor, 1 by j omega CF here. So that's the current that goes in. So I can rewrite this as, note, IIF. What I do is I take V in out. I take V in out from here. So I will get 1 minus V0 by V in, which is nothing but AV, the gain of the amplifier. And j omega CF, I bring it here. Okay. So now, if you look at this one, I can write this expression as j omega CF CMI multiplied by V in. I can write this as V in, where what I have done is I've incorporated 1 minus AV into CF itself. And so we get this expression. And this expression tells us that there is a current which depends on V in, and it is a j omega CMI. So I can model it by putting a capacitor to this node, between this node and ground. Because note, what is the current flowing through this particular capacitor is j omega CMI to V in here. So the idea is that this capacitor has been taken out and replaced by a capacitor at the input. And CMI is what? CMI is nothing but CF 1 minus AV. As long as I say that the capacitor that I put at the input is this capacitor 1 minus AV. Okay, and the two circuits are equivalent. From the input side, the current that flows in for a particular voltage is the same here, and the current is the same. No difference between the two. So now this provides us with an insight that a capacitor connected between input and output appears at the input as if it is that capacitor multiplied by 1 minus AV. Now remember, what will happen is if I look at common emitter amplifier, the input and the output are out of phase. There's 180-degree phase difference. Gain is negative. So if I have an amplifier with a gain of 100, minus 100, what it means is this is minus 100, so this becomes 101. And so what it means is that when I look at from the input side, it appears as if there's an input capacitance which is 100 times CF. That's the insight that it is telling us. A capacitor which is connected between input and output gets multiplied by the gain here and appears at the input here. So that's the insight that Miller's theorem is providing us with. So remember, it may be a very small capacitor, 1 PF, but if the gain is high, 200, at the input side, it appears as if it's 200 picofarad. Okay, 200 picofarad of capacitor. So this is so that's the insight that we get from Miller's theorem, that CMI is CF 1 minus AV. Whatever is AV in your circuit, you get that value. So that's from the input side. Now I'm going to do the same thing from the output side here. All I need to do is say that I know that I get from here and I know that I get from here, both are the same. So we write down I naught. I naught will of course have one component which is going into, let's say, into the amplifier here. Another component goes up, and what goes up is V0 minus V in 1 by j omega CF here. And we do the same thing. We take now, because we are talking about the output, we take V0 out this time, and we write it as 1 minus 1 by AV j omega CF. And this one, which means that I can model it as a capacitor, which has a value CF, 1 minus 1 by AV. and therefore I can get the following. One capacitor here, the other capacitor here. Now, interestingly, what you see is the following. When you look at it from the output side, what we are saying is you can think of it as a capacitor connected between this node and the common terminal here, which is equal to CF1 minus 1 by AV. And we know that in an amplifier, AV is large. 50, 100 or whatever it is, it's a large value typically, which means that 1 by AV can be neglected. So the capacitance between here and this particular node is practically equal to CF. So what Miller's theorem then is telling you is the following. When you look at CF from the input side, it appears as if this capacitor CF is CF multiplied by 1 minus AV, multiplied by the gain of the system, and appears as a large capacitor here. From the output side, this CF appears to be basically equal to the same capacitor because the gain is large and it appears. So CMO, Miller's capacitance on the output side is basically equal to CF. Miller's capacitance on the input side is CF 1 minus AV. So we can use this particular theorem to simplify our circuits here. So if you come back here, so Miller's theorem, where will you apply? You'll apply to a place where a capacitor is connected between input and output. And you'll break the capacitor into two parts, one at the input side, one at the output side here. Okay, so that's where typically you'll apply Miller's theorem. So here, where can we apply? C mu. C mu is connected from the input to the output here. And so what we do is C mu, we can break it up. Note that this is our theorem that we are applying. So we break it up into two capacitors. C mu, 1 minus AV. Yes. I'm only doing it for capacitors, but it's general. For any impedance Z, I could replace it by a Z here, any impedance, and you could do that. Okay, but it's not as simple as so far it's fine, but we'll see later on. Let's go forward and you'll see in a minute. Okay, what is the difficulty in using Miller's theorem? Okay, so C mu we get here, so we replace C mu by C mu 1 minus AV, and we replace here C mu 1 minus 1 by AV. Now recall what is AV. AV is what? The gain between this point and this node. That's AV. We are calling it this node as input node and this node as the output node here. So AV is the ratio of voltage here to the voltage over here. Okay? Not the overall gain versus Vs. No. It's between these two nodes here. It's the two nodes between which the capacitor is connected. It's the gain between those two nodes here. So 1 minus AV here. So far it's very nice. It tells you that the capacitor, the impedance C mu is getting multiplied by the gain here, and this is appearing over here. So it's fine. The next question is, what is AV? How do you find AV? That's where the difficulty comes. What is AV? Now AV, note, AV is what? The ratio of the voltage here to voltage here. Now when you take the voltage will of course depend, the ratio of the two voltages will of course depend on the capacitors that are there. Because we are saying capacitors matter at that particular frequency. So the ratio of these two nodes here depends on what capacitors are there. And to find the capacitors, I need the gain. So that's where I get caught. It was very nice. The theorem was very nice, telling us, it's giving us a qualitative insight that this is what is going to happen to my capacitor. But how do I find AV? That's the difficulty. Okay? Because to find voltage here, I need to take into account all these capacitors, and I don't know these capacitors because they have within them AV also. So if you do that, you'll get a complicated expression and becomes difficult. So that's where the major approximation in Miller's theorem comes, and sometimes errors also arise due to that. And the approximation so problem is AV depends on frequency. So what people do is, they say AV, I'm going to approximate it by its mid-frequency value. We know that gain is going to be a function of frequency, gain between this point and this point. But note that if I neglect these capacitors, I know what the gain is. Gain is minus GM RC parallel RL. So we approximate AV by that value. That's a major approximation, and that's where all the, the errors and all that can creep in. Okay, but let's go forward and do that. So then what we are saying is the capacitor here is equal to C mu 1 plus GM RC dash for us, RC parallel RL here. And the capacitor here, because GM RC parallel RL is large, so we have left the capacitor as it is. There was C mu 1 minus 1 by AV. AV is large, so we've neglected it. So we get now two capacitors. All right. So C mu has been broken into two parts here, one here and one here. Now it's easy. C pi comes in parallel with here, so we can replace them by one single capacitor, which we say is on the input side of the amplifier. So my input side sees a capacitor which is C pi plus C mu 1 plus GM-RC dash. My output side and the net resistance that I see here is RS dash parallel R pi. Okay. On this side, I see C mu plus, if you want to take into account the substrate capacitance here, you can sum it up. So the net capacitor is here, and the net impedance that this sees is simply RC dash here. And therefore, I can obtain an expression for 3 dB frequency. Find out the time constant here, R equivalent times C in and R equivalent times C out. You get two time constants, sum them up, and you get an expression for omega h. Okay, so that's the procedure that we will follow. We know that the Miller's theorem gives us an approximate value, but wherever we see a capacitance connected between input and output, we'll break them. Break them into two capacitors, use this simplified value of gain, which is the gain in mid-frequency region here, and thereby we'll get capacitors at the input side, capacitors at the output side, and the whole calculation becomes very simple. And fortunately, in this case, the expression that you get is similar to what you get using the more accurate methods here. Okay. So that's the procedure for any amplifier that we have. This is what we'll do. Okay. Let me take up this example. Now, what you note here is that if you go back and look at my expression for input time constant, if I look at the expression for input time constant, you see here it is R pi parallel RS dash. Okay, R pi parallel RS dash. Go and look at the expression for RS dash here. What is RS dash? RS dash, if you look at it, is RS parallel RB in series with RB. Now, this is where one has to be careful. In many of the mid-frequency analysis, what I've been doing is neglecting RBB. You know, we ignore RBB, and the model that we have is R pi and GMVB and all that. And which is fine, because what may happen is, let's say RBB is 100 ohms, and my R pi may be 2 kilo ohms. And so I'm okay, you know, neglecting 100 ohms in comparison with 2 kilo ohm as a first order approximation. But now, in high frequency, a trouble comes. And the trouble is, suppose your source that you're using, RS is negligible. You're using a function generator or something, and RS is negligible, right, to drive your amplifier. If RS is negligible, then RS parallel RB will be negligible. And if you're not taking into account an RBB, then what happens is the whole RS dash becomes negligible, right? If you're neglecting RBB, then this is 0, and this also becomes 0. So which means I don't have any RS dash. And if you don't have any RS dash, you can see what will happen into your time constant. Time constant says RS dash is not there, which means you won't get any pole, right? So it starts giving you, so that's the point that I've been trying to make is, in some places, what will happen is, in some analysis, assuming RBB to be negligible is okay. When you're doing mid-frequency analysis and you're comparing RBB to R pi and you say, well, it's small and I'm going to neglect it. In some other place, that approximation doesn't make sense. Because if I now assume RBB to be negligible, then, and if RS is not there, then I will get, you know, the dominant pole is not there. I'll get totally wrong answer. So in this case, in upper cutoff frequency, I must take RBB into account. Especially when I'm driving my transistor through a very low impedance source here. Then RBB becomes extremely important. Otherwise, I'll get totally wrong values of upper cutoff frequency. Okay. So that's why you'll see that, you know, I'm keeping RBB at most places here. All right. So let's come back to the example. So this is the amplifier that we have, 22K here, 6.8 and all that here. So RB is parallel combination here, 5.2K. So we know all that. IC, bias point, how to calculate. All these are given, GM, R pi, R0. The open circuit gain is 232, and with the load of 2.2K is 116 here. Rn, looking from here, is 0.8K. These are all mid-frequency values here. And we know all that, so let me skip. All right, so I'll just skip this here. Maximum voltage swing, we know all that, how to calculate. Lower cutoff frequency, we know this as well. So I'm going to skip this. Okay, let's come back to the upper cutoff frequency. So upper cutoff frequency, the first thing that I need to do is to calculate CPi. CPi has two terms, GM tau F plus CJE. And CJE, we have seen expressions that are there here. So I need to calculate these capacitors. What is CJE? By putting in a base emitter voltage. What is CJC? By putting in the base collector voltage here. So all these values are needed, DC values, to calculate these capacitors. And based on these capacitors, then you calculate what is CPi, which is GM tau F. Tau F is given to you. GM is ICQ by VT here. And so you calculate a capacitance, and it turns out to be fairly large capacitance here. You can see 0.136 nanofarad here. C mu, which is simply equal to CJC here. That's a small capacitor, 0.3 PF here. And then one can go ahead and use the expression here. So you have to do a little bit of calculation to calculate CJE, CJC, and all of that. And then you use your expression for FH, calculate, you get a value of 5.3 megahertz. Now, this is interesting. Note, after getting an expression, you shouldn't just stop here, but you should look at what is really determining my upper cutoff frequency. Why is it 5.3 megahertz? Who's making the largest contribution to my upper cutoff frequency? And that is coming from, if I look at this term, this is the dominant term. Why? Because CPi is large. Note, CPi is a much larger capacitance here, 0.136 nanofarad here. So this is the term CPi is contributing, and this is also contributing a large value here. Note that your C mu, even though it's a small capacitor, 0.3 PF, is getting multiplied by the gain here. So even though CPi is 0.136 nanofarad, which means what? 136 picofarad. This is only 0.3 picofarad. And what was the gain of the amplifier? 100. Right? Approximately 100. So 0.3 PF multiplied by 100 gives us 30 picofarad here. So that's a significant value. So by itself, C mu is small. It shouldn't matter. But because of the Miller's effect, C mu is getting multiplied by the gain, and then it becomes significant. This is also telling you that if you try to increase the gain of your amplifier, if you try to increase the gain of the amplifier, what you will do is you'll have to increase GMRC dash. That's the gain. And as you increase, this term will increase here, and your FH will go down. So there is you can see here a gain bandwidth product. As you increase the gain, the bandwidth or the FH will go down. Okay. So that you can see over here. Okay, so we used a very simple model to calculate our upper cutoff frequency, 5.3 megahertz here. The actual value from simulation gives you 5.67. So it's not bad, it's fairly close to what we estimate using the formula. All right, so I have a couple of other things which I'll ignore here, distortion and all that here. Okay, so we are done with our common emitter amplifier. So let me quickly go over what we have done. Okay, so let's recollect. These are the equations here. What are these equations? This gives us the bias point, collector current. Collector current, how do you calculate collector current? This is the expression here. This allows you to calculate the collector emitter voltage. So these two equations, they tell you how to calculate the bias point. Okay, so that's the first bias point analysis or DC analysis here. This equation we had derived earlier. When you're designing something, it lets you decide how to choose RB or how to choose these values here. They tell you what are the constraints and what are the implications of certain choices that you need to make here. Small signal analysis. So this is all DC here. Small signal analysis. You have expression for gain, your expression for input resistance, output resistance here. These are all mid-frequency values. And we have this expression for voltage swing. Voltage swing is determined by two factors, one from saturation and the other one because of harmonic distortion. And then we have frequency response. Here I've written frequency response determined, lower cutoff frequency determined by CE. And upper cutoff frequency, which we just did, is over here. So that sort of summarizes all the relevant equations for designing a common emitter amplifier. Okay. But that's not the end. The end is not simply to derive expressions and then, set it aside. The idea is to understand. Understand now that you have all these terms that are there, Understanding means, as a designer, for example, you have to understand what are the trade-offs. If I have to increase the gain, what is the price that I have to pay for increasing the gain? Or if I have to increase the swing, what is the price that I have to pay? Or if I have to reduce my lower cutoff frequency, what do I lose? So that's when you can say all of that, when you understand all of that, then I would say, okay, you understand your common emitter amplifier. When you know all the trade-offs, all right, the things that can be exchanged, okay? So let's look at that here. One trade-off we have already seen here, that if I have AV, ICQ, RC parallel RL, we have Rn, which is R pi parallel RB, and we have R naught equal to RC. What I can do is, I can combine these equations into one single equation like this here. All I've done is AV multiplied by Rn divided by R0, and so I get beta 1 by 1 plus R0 by RL, 1 by 1 plus R pi by RB. So I get this here. Now note what your aim is. Your aim is to get, since you're making a voltage amplifier, you would like AV to be high, and you would like Rn to be high, and you would like R0 to be low. So what you're looking for is, in your design in general, you would like to maximize the left hand side. And if you look at the right hand side, beta is a fixed. Let's say once you've chosen a transistor, beta is fixed. So now, if you want to maximize the left hand side, what it says is, maybe you should design it such that R0 is much smaller than RL, and similarly R pi is much smaller than RB. Then if you do that, then the right hand side becomes primarily equal to beta and allows you to get large AV, Rn and R0 here. Okay, so that's one, and it also tells you the exchange that you can do here. If you increase AV, either you pay in terms of input resistance or you pay in terms of output resistance. This exchange will always be there, right? So it tells you the trade-offs between gain, input resistance and output resistance. And it also tells you that maybe when you are designing common emitter amplifier, you should try and keep this term small and try and keep this particular term small in order to maximize the capability of your common emitter amplifier. Now, so if I look at this expression, this term is obviously greater than 1, this term is obviously greater than 1, so I can write this here. AV Rn by R0 is always less than or equal to beta. And so it tells you what I've just said. AV versus Rn will go like this here. AV and R0. If I keep Rn constant, then AV can be exchanged with R0. Alright, if I keep R0 constant, then AV can be exchanged with Rn. There's a trade-off here. And if you don't want to touch AV, then you can exchange Rn and R0. If you increase Rn, R0 will increase. There's nothing you can do about it, at least in this common emitter amplifier. Alright, if you read books, frequently what you will find is, many times common emitter amplifier is summarized by saying it's an amplifier stage which gives you high voltage gain, medium input resistance, and medium output resistance. And the idea is maybe, if I design an amplifier, let's say I have values of 116, so I'm considering 100 as a high value. Medium input resistance, anything around 1K, I'm considering as medium. Output resistance, medium as around 1K or so. So that's a medium value. Again, high, mediums are relative terms, right? So, but frequently, if you, go and read any of the books, you'll find that this is how common emitter amplifier is described. A high gain, a medium input resistance, and a medium output resistance. Now, the question that I'm raising is that a good picture? Do you think this is accurate? Is this accurate? No? Why not? What have we said here? AV Rn by R0. What does it show you? Well, I can get a low input, low gain, and I can get a very high input resistance also. So it's not really true. What this is telling you is not strictly true. Let me show you. So here is a amplifier. Gain is 232, Rn is 0.8K, 2.2K. Here is another amplifier. Gain is 283, Rn is 64K, R0 is 220K. Now, if you consider 1K as low, medium, so we say yes, common emitter amplifier gives you a high gain, medium input resistance, medium output resistance. What will you say about this one? It gives you high gain, high input resistance, high output resistance also. So that statement is not really correct. Why? Because we note that there's a trade-off here. If this is high and this is medium, then this is medium, fine. But I can also do the following. If this is high, and I can make this also high, and then this also will become high, right? So all threes are high. I can do that as well. So a more general, so this is not really correct. A more general thing is what you should, this is a more accurate description of common emitter amplifier. These are the capabilities of your common emitter amplifier. We can also see that I can keep the gain small. Let's say I can keep the gain 5. Nobody is preventing me in designing a common emitter amplifier with a gain of 5, right? And then I can get a gain of 5, and then I can get an input resistance which is very high, and I can get an output resistance which is medium. So I can do that. I can get a low gain, high input resistance, and medium output resistance. And you can do all of these things here. Okay, so you can get low, high, maybe medium. And similarly, you could do low, low, maybe medium. So all kinds of combinations you can do just by looking at this particular expression here. AV Rn by R0 is less than or equal to beta. So there are various possibilities here. So you shouldn't go by this particular point here. The gain is always high, input resistance is always low, and output resistance is also low. Yeah. Here I've shown that everything can be high, high, high. Okay. All right. This is also another interesting thing. So one is this trade-off that you see here. The other one is a lot of the common emitter amplifiers characteristics depends on supply voltage here. And and supply voltage is needed for various purposes. And you'll see how. Note the drop here. So supply voltage, by the way, VCC is nothing but the drop across the resistor, the drop across the collector emitter, and the drop across the emitter, right? That's how the supply voltage is dropping. 3 distinct ways in which it is dropping. Drop here, across the transistor, and across RE. Now what are the implications? If I look at the drop here, we know that gain ICQ RC parallel RL divided by VT is nothing but gain. So ICQ RC parallel RL is greater than or equal to AV times VT. So what are the implications for drop here? Directly affects my gain. The smaller the drop here, the smaller the gain. And the larger the drop here, in general, the larger the gain. Gain is directly related to the ICQ RC drop here. That's one. What are the other implications? The drop here affects my output voltage swing. For a given harmonic distortion, the drop ICQ RC parallel RL also affects my swing here. So this drop is crucial for both gain and for swing. All right, so keep that in mind. This drop now affects my swing. If this drop becomes too low, then my swing gets affected by this particular drop here. So VCEQ must be greater than whatever swing you want plus 0.2 or so. Okay, so this is primarily from swing. This drop affects both gain and swing. Okay, and what about this one? VE, it affects my sensitivity to beta. Sensitivity to beta, and it affects my input resistance also. I can write it VE as, these parameters are given here. We've already shown you RB by R pi here, and sensitivity is 1 by here. Okay. So if I look at now, so these are this thing here. So that's how my supply voltage is dropping. This first part is, this one, I can write it in this form here. AV VT into, these are just taking the same equation and rewriting it. AV VT into 1 plus RL by R naught here. That's the first part, drop here. The second part, VCEQ, I'm writing in terms of VOM. So we put here. And the third part, I'm writing in terms of here, XBS minus 1 VT. So now you can see how supply, this is if you are designing with 5 volt, so your budget is 5 volt, right? 5 volts is all that you have. Now you have to decide this 5 volt, how do I allocate? 2 volt here, 1 volt here, 2 volt here. And what are the implications? 2 volt here, obviously you'll have a certain amount of gain. 1 volt if you put here, then you can't get a swing more than 1 volt. And if you put 2 volt here, you'll get a certain amount of insensitivity. So that's what we mean by supply voltage budgeting here. So as a designer now, you have to decide how much do I allocate here, how much do I allocate here, and how much do I allocate here. And that would depend on what kind of an amplifier you are designing. If you're designing an amplifier, so the specs will be a certain gain value, certain swing value, and these will decide how you budget, how you allocate your supply voltage to this here, or to this here, or to this one here. Okay? So, and what the implications are, you can see clearly. All right. It also tells you now why designing amplifiers with low voltage is difficult. If I have 1.5 volt, something which has to run, for portable applications, 1.5 volt is all that you have. Now 1.5 volt meaning what? I have to allocate here, I have to allocate here, and I have to allocate here. Now where is it going to come from? Right? I would like to make my amplifier insensitive to beta, so I would like to allocate something here. I need some swing here, and I need some gain here. How do I accommodate everything in 1.5 volt? So that becomes the challenge. 1.5 volt or 3 volt, that becomes the challenge of how to do it. Now, gain, let's say if you're requiring a gain of 200, 200 itself will require 200 multiplied by VT. VT is 26 millivolts. If you multiply by 200, you will get 5.2. So now the issue is, I need 5.2 volts to get 200 gain. And I have only 1.5. What do I do? What will you do? I need a gain of 200. I need 5.2 volt supply here. And all I have is 1.5 volt. So what do I do? Gain of 20 will require how much? Gain of 20 will require 0.52. Right? If a gain of 200 requires 5.2, so 20 will require 0.52. So 0.52 I have. I can allocate. So what do? I cascade maybe. One amplifier will give me a gain of 20. Another one of them will give me another gain of 20. 20 into 20. Maybe I can get 400. It's not going to be 400 because this amplifier will load the other stage and all that. Things are more complicated. Okay. So maybe I can get that. So that's how you get more gain, by going towards maybe a cascade of different stages here. All right. So this is an important point to keep in mind. Supply voltage budgeting. How supply voltage affects my different parts of the design. And as you can see here, what are the choices that you have to make as a designer here? How much you allocate here, and how much you allocate. Okay. So suppose AV is 200. So, so these are similar things.